My name is Hudson Gruber. This is Lab 2, Motion of Falling Object. The purpose of this lab is to show the motion of a falling object and looking at the forces of gravity and drag. So during this lab, we'll be using a few formulas. The velocity update formula to calculate velocity, position update formula to calculate the position of the object, and then the drag formula to calculate the drag. And a fundamental theorem is Newton's second law, which describes that the acceleration equals f of net over m, or in this equation rearranged, f of net equals ma. So a preview of this lab is we're going to see that the observed matches more closely to the predicted with gravity and drag. We have the system, which is the paper I dropped, and its surroundings are the air with drag and earth with gravity. So our initial position, we're just going to be dealing with y in the vector, 2.292 meters. And then our initial velocity is 0, negative 0.0445, 0 meters per second. And this was calculated with the first two frames because we needed a average velocity for that initial velocity, which goes with the final velocity of the first two frames. So then we have our delta, which is 0.633, 19, and because this is the total time, and there's 19 frames, okay, in the tracker. And then to calculate b, we first need to calculate the acceleration of the final four frames. So we'll look at a equals the average acceleration of the last four frames, and v equals the average velocity of the last four frames. So then negative 3.21 equals negative 9.8 minus b 5.36 squared, and b equals 0.229. Okay, so our model with gravity. When we put into this code, we have those initial conditions right here, and that delta, but also we have g equals 9.8 and b equals 0. And this is important because b equals 0 because we are not going to be looking at drag in this one. So then the equation is much simpler. It's just f net equals the vector of negative g. And so then this code updates the velocity by doing the velocity plus that f of net times delta. F of net is over m, but because m is 1 and this is gravity, we're ignoring that. And then ball position equals ball dot position, ball velocity times delta. And this just updates everything and plots everything. And the same thing is happening over here, but our b actually has a value this time. So therefore, our f net is going to be negative g plus b times ball velocity y squared. And again, mass is 1, so we're not looking at mass for this. And then our velocity will be updated the same way, and position updated the same way, and everything else updated the same way. So then when we're looking at the graph, everything starts at the same, right? But our observed kind of goes right in between these two predicted. And why is that? Well, the predicted with gravity only, you can see it just accelerates too fast, so it actually ends up touching the ground faster. So it has a stronger slope. And then our predicted with gravity and drag actually looks like it is pretty close. It's just a little slower in falling because the paper kind of sways as it falls. So the coefficient of drag changes, so it's able to fall faster sometimes. Okay, so then possible sources of error during this. Aerodynamics / B not constant because, like I said, that paper sways. There could be air currents from the AC in my dorm. The camera placement is a little wonky, so that could have affected how I click things. And then my phone also had a low frame rate, which caused motion blur, which also made it difficult to choose where the location of the paper was. So what does this mean? Which model, if any, predicts a terminal velocity? So the model with drag actually predicts terminal velocity. If you were to increase the time, you'll actually see the velocity levels out. And what does this mean for net force? Well, with drag and gravity, it will be 0 net force because gravity stays constant, but as the velocity increases, because that velocity squared, the drag increases until it's a constant velocity because they cancel out and it can no longer accelerate, so 0 net force. So what if? Imagine that the object was initially thrown downward Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Actually, yes, the drag, it would be the same terminal velocity. The drag would be larger than gravity, much larger, because of the v is so high in the v squared. It actually will decrease its acceleration until that v decreases enough where drag and gravity are equal. So there would be zero net force, which is the original velocity. And that's it.